Today we characterize the ring of all Gaussian integers Zi. We introduced Euclidean domains, principal ideal domains and unique factorization domains as generalizations of the ring of all integers and the ring of all polynomials over a field. Here we take the ring of all Gaussian integers Zi as a model to show that there are integral domains other than Z and Fx, where a division algorithm can be developed, GCD of two non-zero elements can be found and non-zero non-unit elements can be expressed as a product of irreducible elements. First we develop a division algorithm in Zi. Zi is the set of all elements of the form a plus ib, where a and b are integers, and the products and addition are defined as usual in the field of all complex numbers. Then it is easy to verify that Zi is an integral domain. Now we develop a division algorithm equivalently. We show that Zi is a Euclidean domain. For this, let us define a valuation V from Zi into Z hash, where Z hash is the set of all non-negative integers, by V a plus ib is equal to a square plus b square. So, if we denote a plus ib by alpha, then valuation of alpha is actually alpha alpha bar, where alpha bar is the conjugate of a plus ib, that is alpha bar is a minus ib. So, it follows that for every alpha beta in Zi, valuation of alpha beta is equal to alpha beta into alpha beta bar, which is equal to valuation of alpha into valuation of beta. Thus, valuation of alpha beta becomes product of the valuation of alpha and the valuation of beta. This is a very important feature which does not hold in general, and we will use this particular property of this particular valuation in the future context repeatedly. And hence, if beta is not equal to 0, then it follows from the definition of this valuation V that V beta, that is valuation of beta, is always greater than equal to 1, and we get valuation of alpha beta is equal to valuation of alpha into valuation of beta, which is greater than equal to valuation of alpha. Now, to show that V satisfies a division algorithm, consider alpha beta with beta non-zero. Now, considering alpha beta as elements of C and rationalizing the denominators, it follows that alpha by beta is equal to r plus is, where r and s are two rational numbers. And since r and s are two rational numbers, we can choose integers a and b such that modulus of r minus a and modulus of s minus b both are less than equal to half. Then we can express alpha as beta gamma plus delta as given here, where gamma is a plus ib and delta is beta into r minus a plus I into s minus b. Most interesting is that, which we will see in the examples, that though here it is not clear the expression of delta, but always delta belongs to Zi, that is after simplifying beta into r minus a plus I into s minus b, though r and s are rational numbers, still it will take a form say C plus ID, where C and D are integers. Here we give a theoretical proof that delta is in Zi. Look here, delta is actually equal to alpha minus beta gamma, where both alpha, beta, gamma all are in Zi, and hence alpha minus beta gamma is in Zi. Finally, we get valuation of delta is less than valuation of beta. Thus, alpha equal to beta gamma plus delta is the desired form. Thus, we say that, we conclude that Zi becomes an Euclidean domain, and we know that every Euclidean domain is a principal ideal domain, and hence the ring Zi of all Gaussian integers is a principal ideal domain. And in a principal ideal domain, given any two elements, not both 0, GCD of the elements exists. So, here also GCD of any two non-zero elements exists in Zi. We know that in some integral domains, GCD of two elements may not be unique. Actually, this depends on the number of units, since the GCD are associates. Now, we show that Zi contains actually 4 units, and hence given any two non-zero elements, number of GCD is 4. Here we show that 1 minus 1, I minus I are the only units in Zi. Suppose A plus IB is a unit, then we have some C plus ID such that A plus IB into C plus ID is equal to 1, which implies that A square plus B square into C square plus D square equal to 1. Since A square plus B square and C square plus D square are positive integers, so this implies that A square plus B square is equal to 1, which again imply that either A equal to plus minus 1 and B equal to 0, or A equal to 0 and B equal to plus minus 1. Thus, we get the units as 1 minus 1, I minus I. Now, I give you an example to demonstrate a working method for finding GCD of two elements in Zi. This is analogous to the Euclid's algorithm used for integers. So, let us see how some element in Zi can be divided by some other non-zero element. For example, let us consider 9 plus 5i and 5 plus I. Recall that Zi is a Euclidean domain with the valuation defined by valuation of A plus IB is equal to A square plus B square. Hence, the valuation of 9 plus 5i is 106 and valuation of 5 plus I is 26. So, as we demonstrated in the proof that this V is a valuation, we consider 9 plus 5i by 5 plus I, and rationalizing this we get 50 by 26 plus 16 by 26 I, and here we consider the closest integer 2 to 50 by 26 and 1 to 16 by 26. Thus, we get 2 plus I minus 2 by 26 plus 10 by 26 I, which implies that 9 plus 5i is equal to 5 plus I into 2 plus I minus 2 by 26 plus 10 by 26i into 5 plus I. As I remarked earlier, note that the last term becomes 0 minus 2i, which is an element in Zi, and also valuation of this element is less than the valuation of 5 plus I. Thus, if we divide 9 plus 5i by 5 plus I, then the quotient is 2 plus I and the remainder is 0 minus 2i or minus 2i. We continue this process and finally we get minus 2i is equal to 1 minus I into 1 minus I plus 0. Thus, remainder becomes 0 when we divide by 1 minus I. Hence, it follows that 1 minus I is a greatest common divisor of 9 plus 5i and 5 plus I. Since Zi is an integral domain, so GCD is not unique, and the other GCD of 9 plus 5i and 5 plus I are precisely the associates of 1 minus I. Since in Zi 1 minus 1 I minus I are the only units, we get all GCD of 9 plus 5i, 5 plus I as 1 minus I, minus 1 plus I, 1 plus I and minus 1 minus I. Now, we characterize the prime and irreducible elements in Zi. Since Zi is a principal ideal domain, an element A plus IB is irreducible if and only if it is prime. Now, let us examine some particular elements which are potential enough to be prime or irreducible and check whether these are the all or not. For example, first consider 5. 5 is a prime number, but here we see that 5 is equal to 2 plus I and 2 minus I, none of which is a unit, and hence 5 is not irreducible, which implies that 5 is not prime also. But it can be proved that 7 is a prime element. Suppose 7 is equal to A plus IB into C plus ID. We ought to show that either A plus IB or C plus ID is a unit. Now, A plus IB into C plus ID is equal to 7 implies that A square plus B square into C square plus D square is equal to 49. So, the possible values of A square plus B square are 1, 7, 49, but there are no integers A and B such that A square plus B square can be 7. So, this implies that either A square plus B square equal to 1 or C square plus D square equal to 1, in which case A plus IB is a unit or C plus ID is a unit. Now, we show a very interesting result which states that if the valuation of A plus IB is a prime integer, then A plus IB becomes a prime element in Zi. To check, consider A plus IB is equal to x plus IY into S plus IT, which implies x square plus y square into A square plus T square is equal to A square plus B square. But since A square plus B square is a prime integer, either x square plus y square is equal to 1 or A square plus T square is equal to 1, which again implies that x plus IY is a unit or S plus IT is a unit. But it is unfortunate that the converse does not hold, and that is why we have to go further. To show that the converse does not hold, we consider an element in Zi, alpha is equal to 3i. Note that the valuation of alpha is 3 square, which is not a prime integer. Still, now we show that this element 3i is an irreducible element and hence a prime element. For consider 3i is equal to a plus ib into c plus id, which implies that a square plus b square into c square plus d square equal to 9. But there are no integers a and b for which a square plus b square can be 3. So, the only possibility is either a square plus b square is equal to 1 or c square plus d square is equal to 1, which implies that a plus ib is a unit or c plus id is a unit. Thus, the element alpha equal to 3i becomes an prime element in Zi, whereas the valuation is not a prime integer. Then what? Note that in the particular example alpha equal to 3i, though the valuation is not prime, still it is an associate of the prime integer 3. Recall that there are some prime integers, for example 7, which is an prime element in Zi, and some prime integers, for example 5, which is not a prime element in Zi. Now we see that actually the form of the primes under consideration is the most important feature to characterize the irreducible elements in Zi. For this, we need some lemmas. Our first lemma is as follows: if P is an odd prime such that P is congruent to 1 modulo 4, then the congruence m square is congruent to minus 1 modulo P is solvable. And our second lemma is the famous Fermat's 2 squares theorem. Here we give a proof of this famous theorem as an application of the property. Actually, I would like to include here a proof of this well known theorem just to demonstrate that we are introducing Zi not only as a generalization of Z and Fx, but also Zi has many applications in algebra and number theory. Here we give a proof which use many properties of Zi. The theorem states that let P be an odd prime, then P becomes sum of 2 squares if and only if P is congruent to 1 modulo P. First, assume that P is a sum of 2 squares. Since P is odd, arity of A and B cannot be same. So, if A is odd, then B must be even, and if B is even, then A must be odd, and conversely. Here assume that A is odd, say 2m plus 1, and B is even, say 2m. Then P is equal to A square plus B square takes the form a multiple of 4 plus 1, which implies that P is congruent to 1 modulo 4. Now the converse. Conversely, assume that P is an odd prime which is congruent to 1 modulo 4. Then there is an integer m such that m square is congruent to minus 1 modulo p, which follows from the previous lemma, and so p divides m square plus 1. Now m square plus 1 has a factorization m plus I into m minus I in Zi. Now we show that neither p divides m plus I nor p divides m minus I. If p divides m plus I, then we have some c plus id in Zi such that m plus I is equal to p into c plus id, which leads to the contradiction that the product PD becomes 1, but which is impossible since both p and d are integers. Hence p does not divide m plus I, similarly p does not divide m minus I. Therefore, p is not a prime element in Zi. Since Zi is a PID and in a PID the irreducible elements and the prime elements are the same, so it follows that p is not an irreducible element of Zi, and hence we have some alpha equal to a plus ib and beta equal to c plus id, neither of which is a unit, such that p is a product alpha beta, which implies that p square equal to a square plus b square into c square plus d square. Since both alpha and beta are non-units, a square plus b square is greater than 1 and c square plus d square is greater than 1. Hence, neither a square plus b square nor c square plus d square can be p square. Thus, the only possibility is a square plus b square is equal to p. Now, we are ready to prove our main theorem. For this is an auxiliary lemma. If alpha is an element of Zi is irreducible, then there is a unique prime number p in Z such that alpha divides p in Zi. First note that since alpha is irreducible, it is a non-unit and hence valuation of alpha must be greater than 1. Then by the fundamental theorem of arithmetic, valuation of alpha can be expressed as a product of prime numbers, say p1, p2, pn, which is again equal to alpha into alpha bar. Thus, alpha divides p1, p2 up to pn. Since Zi is a Euclidean domain, so alpha becomes a prime element, and so alpha divides pi for some prime number pi. Now we show that this pi is unique. If not, on the contrary, assume that there is a prime number q which is distinct from pi and alpha divides q. Since pi and q are distinct primes, their GCD is 1 in Z, and since Z is a subring of Zi with same unity 1, the Bezout's identity shows that the GCD of pi and q is also 1 in Zi, which implies that alpha divides 1, which contradicts that alpha is a non-unit. Thus, it follows that alpha divides a unique prime. This is the complete characterization of the irreducible elements in Zi. Let alpha equal to a plus ib belongs to Zi be a non-zero non-unit element. Then alpha is irreducible if and only if it is either of the elements in the following list. It is either 1 plus I, 1 minus I, minus 1 plus I, or minus 1 minus I, or a unit multiple of the prime integers of the form 4n plus 3, or valuation of alpha is a prime number of the form 4n plus 1. Thus, we see that the form of the prime valuation or prime numbers is the most important feature to characterize the irreducible elements in Zi. Let P be the unique prime number such that alpha divides P. Then there is some beta such that P is equal to alpha into beta, which implies that P square is equal to valuation of alpha into valuation of beta. So it follows that either A square plus B square is equal to P or A square plus B square is equal to P square. Since P is a prime number, P cannot be a multiple of 4, that is P cannot be congruent to 0 modulo 4. Hence, we have only 3 cases. One is P congruent to 1 modulo 4, other is P congruent to 2 modulo 4, and the third condition is P congruent to 3 modulo 4. Let us consider case 1 when P is congruent to 1 modulo 4. In this case, P is of the form 4n plus 1. Since the valuation of alpha is P or P square, so it is sufficient to show that valuation of alpha cannot be P square. Then it will follow automatically the valuation of alpha is P and the P is of the form 4n plus 1. On the contrary, assume that valuation of alpha is P square. Then we have valuation of alpha into valuation of beta equal to P square, which implies that valuation of beta is equal to 1. Thus it follows that beta is either of 1 minus 1 I minus I. Now alpha bar is equal to P square is equal to alpha beta whole square implies that alpha bar is equal to alpha beta square, which is again equal to plus minus alpha. This contradiction shows that valuation of alpha can never be P square, and so A square plus B square is equal to P. Now come into the case 2 when P is congruent to 2 modulo 4. It is easy to observe that in this case the only value of P is 2, and so either A square plus B square is equal to 2 or A square plus B square is equal to 4. Since A, B are integers, the latter case cannot occur. Thus A square plus B square is equal to 2, which implies that A is either plus minus 1 and B is either of plus minus 1. Hence alpha is either 1 plus I, 1 minus I, minus 1 plus I, or minus 1 minus I. Our third case is P is congruent to 3 modulo 4. Then by the Fermat's 2 squares theorem, A square plus B square equal to P cannot occur, because this theorem states that a prime can be sum of 2 squares if and only if it is congruent to 1 modulo 4, and so valuation of alpha is equal to P square. Then valuation of alpha into valuation of beta equal to P square implies that valuation of beta is equal to 1, forcing beta to be a unit in Zi, and then from alpha beta equal to P we get alpha is equal to P into some unit U. For the converse, first assume that alpha is equal to UP, where U is a unit in Zi and P is a prime number of the form 4n plus 3. Let alpha is equal to beta gamma, where beta gamma are in Zi. Then valuation of alpha is equal to valuation of beta into valuation of gamma, which implies that valuation of beta valuation of gamma is equal to P square. Since P is congruent to 3 modulo 4, it follows by the Fermat's 2 square theorem that valuation of beta is not P and valuation of gamma is also not equal to P. Thus either valuation of beta is 1 or valuation of gamma is equal to 1, which implies that alpha is irreducible. For the other two cases, it is sufficient to note that V alpha, that is valuation of alpha, is prime, and hence it follows that alpha is irreducible. Thus, we discussed a division algorithm in the ring of all Gaussian integers. You all know the division of integers and division of polynomials over a field. Here you learn division of a new object, namely Gaussian integers. Also, we have a complete characterization of the irreducible elements in Zi. Now, I left it to you the problem of expressing every non-zero non-unit element in Zi as a product of irreducible elements in Zi. Please do it yourself without any help.